Hi everyone. How about making unimaginable possibilities become tangible realities with mind-bending capabilities, intelligent algorithms, and data-driven insights? Quantum computing and AI are paving the way for solving complex problems with unprecedented speed and accuracy. Please welcome our next speaker, Abhishek Chopra. Abhishek is an accomplished entrepreneur and a researcher specializing in the fields of computational sciences and quantum computing. He holds a master's and a bachelor's in aerospace engineering. With multiple awards, research papers, keynote sessions under his belt, Abhishek has established himself as an esteemed figure in this industry. Abhishek today will be talking about his startup, BosonQ Psi, and the stimulating quantum realm. Please welcome Abhishek.
Thank you, Trupti. Really appreciate for the kind introduction. Myself, Abhishek Chopra, founder and CEO of BosonQ Psi. Let me start sharing my presentation as well. Trupti, can you confirm if you can see my presentation?
I can, Abhishek. Yes, please.
Okay, great. So really excited to be here in this amazing community at DTIA. And I will be talking about what quantum computing is all about and what at BosonQ Psi we are doing. Before starting on, just want to give you a little bit of information about BosonQ Psi itself. We are an enterprise SaaS startup based out of US. Also have presence in UK in Cambridge and in India in Bangalore. What we are basically doing is we're developing the next generation simulation software BQ5, which leverages the power of quantum computing to solve very complex simulations that exist right now. This is to reduce the time, increase the accuracy, and reduce the cost we do to these simulations. We are working right now for the automotive industry. We will also have plans to go into the aerospace manufacturing and energy sectors. Currently, we have completed two POCs with BMW and Maruti Suzuki, and then we have about 12 or so enterprise customers in the pipeline. Raised 1.1 million in private equity and also government grants of about 670K. Now, why so much interest around boson QSI? Why everybody wants to, work in this area of quantum computing? Let me tell you why. The most basic reason, around ourselves right now, we see so much of computing happening, especially with the generative AI, how much it is taking leaps and bounds right now. The question always comes down, where will we get more computing power to do so? One of the ways to do is, logically speaking, is to make the systems much more larger. That's how we have come from chip to making high performance computing. That's what Nvidia is doing, Intel is doing, and others like AMD. But we are bottlenecked, or we will be soon bottlenecked by the electricity requirement and the real estate requirement. It has been said that to run the biggest supercomputer of the world, it would take 2 days of electricity of a city like Mumbai to do so. So that's not really the way to go. So the other way to do is to make your chips that are there in the given real estate, how to fit in more chips, so reduce the size of the transistors, and that's what we have been doing. That's what the whole um, like laws that has been laid out in the computer science realm has been doing. But now we have reached nanometer scales, which restricts us from reducing it more. Not that we cannot produce these chips, but the physics that will start to apply onto this is no more classical physics. It is quantum physics, and hence the transition to more powerful computers at much smaller scales of its foundation is what quantum computing is all about. So a lot of people might have heard about this so-called term of quantum computing. It is dictated by two of the phenomena, I would say, in this field. One of the physics for of phenomena is called quantum superposition, and let me explain you on how this is different from classical. Classical systems like your computers right now, or your phones or your smart watches or anything like that works on this phenomena called bits, where all the information is strings of zeros and ones. So there's only two possible: there's black or white or zero or one. That's how things are. But quantum presents you the opportunity that the world is not just black and white; it's shades of gray in the middle. So what it says, it's not just zero or one, but through something called as qubits, there are a lot of possibilities that you can process information between 0 and 1. So 0, 1, and things in between that. And that is what the utilization of this superposition is leads to the quantum superposition, where we say that the information can be in multiple states at a given point of time. So it doesn't have to be just two, like just 0 or 1. It can be any state, and hence you can store more information. Let's see how this is helpful. Let's say in this map that I'm showing on the right hand, you want to go from home, which is on the blue side on the top left. You want to go to the school, which is on the bottom right. um, Classically speaking, you will be traversing each path that is there to know what is the quickest path from going to home to school. But what quantum allows is it energizes all possibility, and then it finds which is the possibility which makes me go the fastest from home to school. So that's what the quantum superposition helps. Now let me say that on the bottom right, I want to go from just this small four possibility to many more possibilities. How will I do so? So I will need to add more qubits to it, which is what is led by quantum entanglement, which is the next uh, physics phenomena. And what it does is, as the information grows, we need the quantum entanglement. Quantum entanglement is simple to explain. Um, in some magic, you can say it's said that if you have one qubit and you have another qubit, and how much ever they are far apart, if you turn one qubit, the other qubit which is entangled with it also will turn, and hence this leads to something called as um, 2n qubit representation, meaning let's say you have two bits in classical, that can be represented in four ways in quantum. If you have six, you have 2 to the power of 6, and it grows exponentially. So that's where what's the difference between quantum computing and classical computing is, and that's what leads to the benefits. Now, one myth that people have is quantum computing is great for everything. No, no, no. Just like how CPU existed and then GPU came along, but some tasks are better suited for GPU, same way QPU will come along, and QPU is suggested to be used for certain tasks which cannot be done very well by the classical computing side of things. But the whole tech stack in the future will look like CPU, GPU, and QPU, not just QPU. So now let's look at what this quantum computing stack really means. Let's say you are at a user level. Let's start from the very fundamental, the hardware. These are the companies which are working in the hardware. There are different types of ways you can make quantum computer, and to make quantum computer, you need different types of hardware component. Just like how you need semiconductor, the whole supply chain, quantum has also its own supply chain. Then you have the middleware, which really translates the things at what you see in like Windows level, for example, how you convert the classical information to quantum information, and there are many companies which are also working on that. And then come the application layer, which is the most closer to the user level. And these are the different types of simulations people are looking at: drug discovery, financial, chemical, optimization, logistic, and BosonQ Psi also is realized in this one, the top, if you see. Now, these are the companies which have already invested a lot in quantum, and they are looking at what are the future possibilities that they can go, especially in, you can say, like the sectors that I talked about: you have automotive, aerospace, financial sectors, logistics, supply chain. Everybody's testing out what they can do with quantum, even though it's far where we can explore and get ourselves ready for the day the quantum computers will be ready. And here are some of the applications that are our interest right now. There are six possibilities that are shown here. I will focus more on these two possibilities: engineering simulation and traffic optimization. Now, one thing I do want to mention here before I go on to these applications, that the world of quantum computing is not just quantum computer, it also is quantum information science. quantum information science really dictates the mathematics that exist, which can be done very, very well on quantum mechanical systems such as quantum computer, but they too are independent of each other. Why I'm mentioning that is because there is a possibility where you can exploit the mathematics of quantum information science to develop quantum
Mhm.
algorithms which will fit into your HPC right now. Like you can run those things on the current HPC. You don't need a quantum computer for that, which is what BosonQ Psi is doing right now. When the quantum computers are ready, these same quantum algorithms can go and run on those quantum computer system, and it will give you much more benefit. So now, taking that into account, one of the first use cases I wanted to
Abhishek,
showcase.
if I may just interrupt you, I have a
Sure.
few interesting questions which have been coming up in the Q&A session. So
Mhm.
before we jump into the use cases, would you like to tackle a few of them about the quantum computing technology per se,
Oh, like
or
what are
would
the
you?
different architectures?
I'll just quickly go through one of the questions. So essentially, the
Mhm.
question is, what is the concept of simulating quantum realms, and why is it considered the next frontier of exploration? Of course, I think you did just mention how about from bits we're also adding the cuboids, and the whole interlinking of that
Mhm.
is what is the raised to power is what is adding to the whole power of the simulations that we can do. If you could just probably speak a little bit more about that.
Sure. The why it is considered the next frontier is because, like I said, in the initial side, we are bottlenecked by what we can do today, and in some of the problems, such as NP hard problems and others that are out there, we still don't have the ability. Let me take a very simple example, which is very intuitive. Cybersecurity, which I'm also displaying here in this one. Uh, right now you have this 256-bit encryption that is there in your mobile phones and everywhere. That's the
Right.
standard right now. um, if you put into the 2 to the power of thing, I think so it will be some like 10 or 8 or 10, something like that, number of qubits that it will take to break the encryption, like logical qubits as spoken. Now think about when you what will quantum allow in cybersecurity. um, you have a system which is probabilistic in nature, means it keeps changing its activity. There's no set thing. So when you have something encrypted which is quantum, meaning either it can work two ways. Number one way, it is that it is like offensive side is uh, you have a 256-bit encryption. Now quantum, because it can explore so many possibilities, which is inherently parallel system, it can break 256-bit encryption very, very easily. Once we are there with that, like once we have the technology, and that fear promotes that you need to have an encryption which is actually not 256, but it is called PQC, post quantum cryptography, where you can protect something which is like attacking the thing that you're protecting. So that's where you have this phenomena of, like I gave qubits, like zeros and ones flipping between each other. If you start to do that way, it will actually not be able to easily predict what your thing is, because these systems are inherently random in nature.
Sure.
Does that help?
It definitely helps it. Thank you so much.
Now, going into the first use case of engineering simulation, that's what BosonQ specializes in. We did this POC as part of Maruti Suzuki work with them. Here, we took a simple example to first showcase that engineering simulations can actually be performed using quantum information science, and actually can scale up from there. So this what I'm going to showcase. On the right hand side, you will see the diagram which is showing the orange part, which is basically called control arm. It's made out of aluminium, 4 in number, because it is attached to each wheel. The objective here was to reduce the weight while keeping the durability high. Now, why this is important? Because as we are going into the EV realm of thing, the more lightweight your car is, the better your range of your car would be. So now, here what we did was, there was an initial input. This is an input which is very similar to traditional simulation software. Came into our software, we went through the process and we optimized the design. which you can see on the right hand side. The more interesting part is we compared this with the classical simulation software, and what we achieved was 7% more weight reduction at one-eighth of the HPC cost, which translates to about 500K of dollar of material saving and about 29K of HPC cost saving. This is by giving something which is quantum in nature, and the quantum algorithm allowed it to become faster, better, and economical. Now, this
Correct.
is just a small use case. What
Mm-hmm.
it could scale up to is a possibility here, which I talk
Mm-hmm.
about in potential use case. So this is what the team is working right now in simulating um, the chassis of the car during crash. Now, why this is
Okay.
important is because the safety and the robustness of the thing. So here, what we did was we exploiting the extrapolating the results from the previous slide. If we talk about the same one order of magnitude saving that our algorithms can do, we are talking about 1.2
Mm-hmm.
billion dollar of material saving and about 50 million of saving from HPC cost. And last that I want to talk about is the airline route optimization use case. Again, optimization is another set of problems that quantum can do really well. We did this POC where we took 100 flights over Europe, and the goal was to reduce the carbon footprint, fuel consumption, flight time by by making the most optimized route in a 3D space. And what we compared our results of the quantum search algorithm with the classical algorithm, and we found that we can reduce carbon footprint by 18% compared to the classical version, 4% fuel consumption, and 1% flight time. And this is great, and we're looking for airlines to us to do this, to scale this up. This is the final slide where I'm talking about the roadmap of BQP. So we have two types of simulations. We have optimization mathematics and we have partial differential equation mathematics that BQP is trying to simulate. And
Mm-hmm.
what this, how we are doing this is today we are doing this with so-called quantum-inspired approach. The quantum-inspired algorithm gives one order of magnitude, and what it really is, as I described, we are exploiting the mathematics coming from quantum information science to be able to simulate it on HPC. When the quantum computers are more mature, we will go into the hybrid system and then eventually to the fault tolerant system. And this is the timeline that we are working with and the kind of things we will be bringing in as we go along. So to conclude, quantum computing is next in line technology, both speaking by science and engineering way. Qubits are powerful because of its two properties that we talked about, and the quantum stack is rapidly growing. There's a lot of companies working in different sides of things, and there's a major player who has started experimenting with quantum, as we saw the end user list, and also the huge investment coming both from the private and the government side of things. Now, quantum, again, I do want to remind everybody, quantum can do certain class of problem very well. Not everything, but certain class. And some of those interesting application I talked about here in this way. So thank you, everyone. I'm happy to take any questions.
Yes, of course. We do have some very interesting questions here for you, Abhishek. Let me just quickly take this one. What are the main techniques or approaches used to stimulate quantum realms, and what are their strength and limitations? Wait, yes, you did, of course, just cover one of them. Maybe if you could give us insights over a few more.
Yeah, I'm not sure about the scope of the full question, but I will take it in broader sense. There's one way to do it, as I mentioned, quantum inspired algorithm. A lot of the uh, I should not say a lot of few companies are trying to utilize the mathematics and taking for different applications. We have companies in finance sector, biomedical side of things, which they are utilizing this quantum inspired. This is uh, useful uh, because a lot of people are promising quantum, but nobody is able to showcase it because the quantum computers are not ready,
Right.
and which is like with any technology that is out there.
Correct.
But we
Absolutely.
can exploit this, in today's HPC we can simulate that. Now when we are simulating quantum, there are different ways. You can do that the way BosonQ Psi is doing, which is like taking the mathematics, running it on HPC, or you can use quantum simulators like the ones that are out there by Fujitsu,
Okay.
Toshiba, and others. Uh, and then to really test out, so what will quantum algorithms behave on a quantum computer, you have simulators by the quantum hardware providers as well.
Correct.
That-
Okay. So that's fine. Perfect. Abhishek, another question that I can see is while, of course, quantum computing is an integral part of deep tech, how does it go? correlate, or how does it intertwine between the other deep tech key components, like, for example, AI? I mean,
Yeah.
data, of course, I do understand that's the core, again, something on which quantum computing is built, right? Could you just maybe spend a few minutes on that? If you would.
That's a very great question. Now, any field that is out there in deep tech, AI being one example, you can talk about drug discovery, biomedical, you can talk about anything on the finance, fintech uh, side of things. All of them are relying on computing as their base in some or the other way. Some more like AI, which is everything is all about computing and simulating. I want the folks to think of quantum as that enabler. It is an enhancer to what is
Correct.
already existing. For example, we are doing, and my slide also showcased that one line, and I just want to highlight it. We are working on, for example, quantum neural network, which is a way of quantum machine learning. Now, again, we are taking classical machine learning, putting into quantum realm. You can put anything onto quantum realm, given that you are following that mathematics that it really
Right.
benefits from.
Right.
So, I don't want people to think of quantum as yet another deep tech area. It is much more
Correct.
fundamental. It's a computing layer
Okay.
where you can enhance your current processes much more.
Right, right. So it wouldn't be wrong to say that we would need to lay a foundation, which essentially would be an data and an AI-led foundation, on which we would end up, on which ideally we should be building up the quantum computing layers, right?
Yeah, it's opposite, but you're right. Like you
Okay,
need to have the quantum computing foundations, algorithms, middleware, and hardware to be able to do
okay,
AI and data analytics and other things more
okay,
faster.
okay. Right, yeah. So it would, like, correct. It would feed into it, but right, yeah.
Mhm.
Fair enough. I think that definitely clarifies. Uh, a few other questions. In the interest of time, I do have 2 minutes, so maybe I can just quickly pick up one more. Okay, this one sounds very interesting. Which industry segments are early adopters, and what are the near future trends?
Yeah, that's a very good question. I would say the biggest benefit that people are trying to get is out of biotech. The reason being to simulate molecule, which is a very computationally challenging problem for classical system, and quantum just right like fits into that because of its inherent probabilistic nature. That's a very good field people are exploring. There are some very good work going on. The other area is fintech, like portfolio optimization. Some of these things people have shown. So that's another area. And the third is the mobility sector where BQP is working, which is aerospace, automotive, manufacturing, and those side of things. There are many industries which can benefit from this because of the cross, you can say, application area. But these are the ones which have really stood out. And when I was also showing the investment going into this field, these are some of the ones that you can see here.
Okay, fine. Abhishek, one more question wherein I would want to put on the hats of the actual, the manufacturing industry, who would, I definitely understand, would be of, for whom this would be of great interest. Does it have, is scale important to have, to see the fruits of quantum computing, or to have the benefits of quantum computing? How important is scale?
It's very important. I think so. We are able to do some problems in the manufacturing realm today, but those problems are limited. We really would like to have more number of qubits or quantum computers with more number of qubits. Higher
Okay.
quality of qubits is also very very important. So both quantity and quality is of utmost importance. So this becomes more of a science and engineering problem which people are trying to solve. But once we have the scale, and it happened with the AI revolution, I've seen it grow in front of me in my lifetime, I would say, and I'm young still. I would say I'm 26, right? So I've seen from 2010 how the AI has picked up, but it was always called hype, and the technology was not ready. We are not seeing something useful. But for those who were patient enough, we are seeing the glimpse, I would say, the early stages of AI revolution with Gen AI, what it is able to do, and things beyond. Same thing will happen with quantum, but when it will happen, it will be much more bigger, I would say, and everything will be, will start to look different. Yes, the world, the scale when I talk about will not be where your mobile phones will be fitted with quantum computers. That's a little too far. Not saying that it's not possible, it is, but it just, we are talking about a realm of like maybe 20-25 years, so we will get there. but but again, quantum is not required for everything. Quantum is required for the most computationally
Absolutely.
extensive calculations, as I mentioned, cryptography, when you're solving big fluid dynamics problem, climate, carbon capture, going to different planet, where you really require that massive. That's where quantum will be really helpful. So the world will look like CPU, GPU, QPU, and the advancement on CPU, GPU, TPU, FPGAs will help the advent of QPUs as well, I would say.
Absolutely. Thank you so much, Abhishek. I do have a few more very interesting questions, but in the interest of time, I think I would have to close the session. Thank you so much. It was amazing to hear about quantum computing and in this lucid language that I mean, it's been a pleasure. Thank you so much.
Great. Thank you so much, Tripti and Sandy, for inviting me here. I'm also happy to drop my LinkedIn link in the chat, so that if anybody has more
Absolutely.
questions, I'm happy to answer those. So thank you
Sure.
so much,
We
everyone.
also have, yeah, thanks, Abhishek. We also have some polls which we've just opened up. Please feel, for the audience, please feel free to go and use those polls.